Yeah, okay. By the way, that was a great talk before this one. I like especially the impact on society, because I think as cybersecurity specialists for CPSs, I think that's really one of the main focus of cybersecurity. So I'll move on to my own presentation now. And so I'll be introducing very briefly cyber physical systems. I know it's not really necessary, we're all experts, but for the sake of the presentation, I'll then move on to the research approach that we've adopted in this work, and then the test beds that we've used as case studies. I'll then talk very briefly about the system modeling approach, which is essentially the foundation of our work, followed by the attack detection framework and also the detection mechanisms itself that we've used. After that, I'll be elaborating a little bit on the threat models that we've considered and also evaluating the performance of the detectors on some of the attacks that we simulated on our test beds. And lastly, I'll present some of the conclusions of our work. So let me begin with cyber physical systems. Like we all know, these are basically forming the foundation of urban critical infrastructure, and they comprise of many interconnected components like PLCs, sensors, actuators, the SCADA workstation, and the HMI, and of course the glue that binds them all together, the communication network itself. And as we saw in the earlier talk as well, and we know very well that this communication network, while it helps the components actually interact with each other, it also exposes the entire system to malicious entities. And this is especially crucial for cyber physical systems because they not only affect the system in general, there are surrounding economies which are dependent on the functionality of these cyber physical systems. So this actually makes the security measures for CPSs a lot more complicated than standard IT procedures, because the attacks can be in both the physical domain as well as the cyber domain. So in our work, we actually perform case studies on a water treatment and a distribution plant, wherein we take in a model-based approach into consideration. So like I mentioned, the motivation of this work is to carry out exhaustive testing of detection techniques for CPSs using different test beds, and then actually comparing their efficiency to see which techniques can be used under certain circumstances of attack. Now, the detection mechanisms itself that we've used are of two types. Firstly, the statistical methods, which include the cumulative sum or the CUSUM detector and the bad data detector. And the second type is a device fingerprinting technique called NoisePrint. I'll be elaborating on these techniques later on in the talk. So let me just give you an idea of the methodology that we've used. So the idea is to model the entire test bed or the entire CPS as a mathematical system. Using this, we can actually get an idea of the estimated or expected behavior of this plant under normal circumstances. So now we have an estimated behavior, we have the actual data readings that are coming in from the plant at real time. When we compare these two, we're able to obtain a residual. This residual is then analyzed by our detection mechanisms to kind of decide whether or not the process is running normally, which it should during the absence of attacks. And when when the system is under attacks, we expect this residual to kind of show deviations. So like I said, the detector is essentially supposed to catch an attack when the expected behavior deviates far too much from the expected behavior. Now, let me give an overview of the test beds that we've used. The first one is called SWAT, and it stands for Secure Water Treatment. It's essentially an operational scaled-down version of a treatment plant. And you can see in this architecture, the entire system is actually divided into 6 different stages, each of which are performing a different process. And of course, each of the stage has its own distinct PLC, which is helping the processes within that stage run smoothly. You can see that each of the stages also have their own set of sensors and actuators. And these are essentially the target points of the attacks that we are taking into consideration in this work. The LITs are essentially level sensors, and FITs are flow sensors. I'm just explaining the terminology, so later on you can know exactly what I'm referring to when I talk about specific attacks. The MVs and pumps refer to the valves, and the MVs and Ps refer to the valves and the pumps respectively. The second testbed we used was a water distribution plant called WADI, and it serves to it serves to represent the actual water distribution networks that we find in cities today. Similar to the SWAT, even this particular plant is divided into several substages with a dedicated PLC for each, and also their own set of sensors and actuators that make up the whole system. Now the maths part of this whole work, which is the system modeling. So it's essentially a simple concept, even though it looks very, it sounds very complicated. The idea is to treat these test beds as a multi-input, multi-output system. So the system sensors actually act as the output of the system, because we are able to know whether or not the plant is running smoothly when we take a look at these sensor readings. So we treat this as the output of the system, which is the Y in the equation. And in fact, these sensor levels are actually governed by the control actions, which in turn change or alter the states of the actuators. So these actuators are actually taken as the control input, which is the U in the equation. So for both of these test beds, what we essentially did was we ran the plants continuously for a really long time under normal operation, so that we covered all possible modes of their functionality. And we obtained this large data set, and we ran some subspace system identification methods on it, and we obtained a system model of this particular form. The idea behind doing this is now we can describe the entire system in terms of a mathematical model. We are able to obtain some expected or estimated states, because now we know the exact dynamics, and we have a quantitative way of actually expressing it and getting a so-called normal expected behavior. So we actually validated these system models using a standard root mean square method. This is simply to kind of check whether or not the models we've created are actually even accurate enough. And you can see in the table that these are pretty much precise in terms of the RMSE values. We also performed a visual validation of the models, and you can see that under normal operation, the residual actually averages around 0. So which basically the idea of this is to conclude the fact that these models that we've obtained are actually can be implemented under normal circumstances. Okay, after that, let me describe the attack detection framework. So what this means is how exactly are we performing the detection of attacks? How exactly are we using these models and detectors in the whole endgame? So the idea is to use these two steps. Firstly, we use the system models, we get the estimated sensor readings or the sensor output, system output, and then we get the residual between the actual incoming readings, as in the real-time sensor readings, and the predicted sensor output using our system models. And then once we have obtained this residual, we use our detectors to actually analyze these residuals and check whether or not the system is under an attack. So the idea is like I mentioned, so the residual is essentially computed by taking the difference between the actual sensor reading and the estimated reading. And like I showed you in the earlier graph, we expect this residual to average around 0 under normal operation. But when there is an attack, we would expect the residual to kind of have a bias. So it won't be averaging around 0. And therefore, these are the hypotheses that the detector is actually testing constantly to decide whether or not the plant is under an attack. Now let me move on to the detectors itself. The first one is called cumulative sum, or CUSUM. It's essentially an algorithm that takes in the residual vector as its input. Now this residual vector serves to act as a distance measure between how far the estimate is from the targeted mean. So it's constantly checking whether this distance measure is deviating, and once it deviates at far too much or beyond a certain threshold, it raises an alarm and kind of informs the operators of the presence of an attack. Now this window for error, which is how far can the distance measure be allowed to deviate, it can be tuned based on your particular system using the slack variable kappa, which is here. And finally, the threshold itself must be tuned in such a way that you account for certain false alarms. Now, why I mentioned false alarms, I'll be talking about that a little later, but that point is to keep in mind that these detectors have to be designed specific to your system such that it is able to give you reasonable accuracy. At the same time, it allows it keeps room for certain glitches and technical aberrations. The second detector is called the bad data detector. It's a very standard detector. It's used widely across CPS security literature. And it essentially it constantly checks whether or not the residual of the estimated and the actual is within a certain threshold. And as long as it does not raise an alarm. The second it crosses that particular threshold, it raises an alarm, and therefore we know whether or not the system is under attack. The last detector we have is called NoisePrint. It's basically a sensor fingerprinting technique, and it works on the principle that this residual vector obtained from the system model is actually a function of the sensor and process noise when the system is in steady state. So the idea is to kind of have a profile of each of the sensors and each of the processes based on their noise, such that we obtain a fingerprint of this entire system under normal operation. So this particular detector involves the following steps: residual collection. Like I mentioned, the residual vector for each of the sensors is obtained from the system models. This entire data set of the residual vector is then divided into chunks. And this is done basically to ensure that the machine learning models are able to get well trained. And lastly, we perform feature extraction, which is essentially analyzing these residuals in the frequency and time domain and obtaining their attributes such as the skewness, the kurtosis, the standard deviation, and so on. And we use machine learning techniques to kind of create a fingerprint, which is constantly checked when the plant is being run under normal operation. Now, let me elaborate a little bit upon the threat model. So based on the execution of the attacks, we can classify them into these three forms. Firstly, the single point attack, like the name suggests. In these kind of attacks, you usually have just one point in the whole system which is used as a target. A multi-point attack would have simultaneous target points. And a stealthy attack is essentially one that tries to stay inconspicuous to detectors. It involves very minute alterations or perhaps periodic alterations, and the idea of this attack is to kind of pass completely undetected, especially when statistical detectors are used. Now, these attacks itself can be single stage or multi-stage. By that, I mean that we all know in CPS systems, they are large systems with different processes taking place in different stages. So the attacks need not be confined to one particular stage. Based on how competent the attacker is, how much damage he or she intends to cause, these attack points can be spread across different stages. So these three types of attacks are the kind of attacks that we try to simulate, or we have simulated on our test beds before using our detection methods to check how well they can actually catch these attacks. Now, following this, so the idea is that these attacks itself, based on the type and the nature or the intention of the attacks, we can classify them into two types: the bias injection attacks and the stealthy attacks. So when we talk about bias injection attacks, the idea is to kind of send spoofed values to the PLCs. So when the PLCs itself are getting incorrect sensor readings, obviously the actions and the control decisions that it takes based on these readings will also be incorrect. So the idea is to cause harm to the system by sending in incorrect sensor readings. How they do this is they usually change the value of the sensor by a certain amount, which is given by delta. And therefore, this new spoofed value is what the PLC kind of reads and takes decisions based on. Now, stealthy attacks, on the other hand, the idea behind the concept behind stealthy attacks is that this attack vector or delta is chosen in a way that it passes undetected when statistical detectors are used. I'll be giving examples of this later on, which will probably make it easier for us to understand. But the idea is to stay inconspicuous to statistical detectors. Now, this table shows the different attacks that we have actually simulated on the SWAT test bed. So let me just point you to these two attacks. So the first one is essentially an example of a stealthy attack wherein we change the value of the level sensor, which is the level of water in the tank, gradually by 1 millimeter every second. So now, even though the actual LIT is kind of changing in a completely different way, what the PLC reads is a constantly increasing level at every 1 second. So this spoofed value is now what the PLC uses when it decides its control actions. The second attack is a simple bias injection attack wherein the original value of the level sensor is changed to another value. You can see actually most of these attacks are examples of bias injection attacks, but for the sake of demonstration, I have just highlighted this one. So let me move on now to the performance metrics. So in order to actually evaluate our detectors, we've used these three attributes. I'll be explaining them now. The first one is called the TPR, or the true positive rate. Like the name suggests, it's basically the number of times a detection mechanism correctly raises alarms over the course of the attack. The false positive or the false alarm rate, which I spoke about a little before, refers to the tendency of the detection mechanism to incorrectly raise alarms in the absence of an attack. So what this means is that even under normal operations, there are times when the sensor readings can be such that the detector is deceived into believing that there is an attack. And in such events, it raises alarms incorrectly, even though there is no attack taking place on the system. Lastly, the time taken for detection, like the name suggests, it is essentially how long a detection mechanism takes to kind of raise an alarm. Now, the TPR of a technique is a direct indication of its attack detection accuracy, and we want this to be as high as possible. The FPR or FAR, on the other hand, it represents its tendency to raise false alarms, like I said, and this is very, very inconvenient in practical scenarios because in actual industrial plants, we're talking about huge systems with countless sensors and countless actuators that have to be checked. So if a detection mechanism is raising way too many false alarms, as an operator, it's far too tedious for me to go around checking these sensors. So we want the FPR to be satisfactorily small. Now, a high TPR or a high true positive rate is not really very beneficial if the detection mechanism takes far too long to detect the attack. Because like I said, when we are talking about it, like we all know that in a realistic sense, these CPSs are performing processes that affect economies, that affect consumers in a very crucial way. So if an attack goes undetected for a really long time, even in that window, it is capable of causing harm to the system and the environment around it. So we want this TTD, so to say, to be reasonable in the sense that it should be able to detect an attack fast enough for it to be mitigated before causing any kind of significant harm. Now, in a real life scenario or actual scenario, there's usually a trade-off between the TPR and an FPR. What this means is that you could have a very high FPR, as in the detection mechanism is actually raising way too many false alarms, but it is also extremely efficient at detecting attacks when there actually are attacks. Similarly, you could have a technique that does not raise any false alarms or has a very low false alarm rate, but it tends to miss out on certain actual attacks when they happen. So the idea behind this is you want to have a perfect balance such that you have a reasonable, you have a satisfactory TPR while having a kind of feasible FPR. Now, we tested these detectors under normal operation as well, because it is important to know whether or not the detector is actually raising too many false alarms or no. So these are the results that we obtained. It's a very too many numbers here, but let me just highlight the false alarm rate. So you can see that the false alarm rate is significantly lower in some cases. Now, the idea behind having even this much of a false alarm, which is 5% or even 2% of false alarms, is to allow the detector to account for temporary abnormalities, which are caused by technical glitches or external disturbances, which are actually very common in practical industrial plants. This particular graph also shows that the residuals actually lie within the threshold. So the idea behind this is to conclude the fact that the detection mechanisms actually perform pretty well on both the test beds under normal operating conditions. Now we move on to the detector performance under attacks. So this table shows the different attributes, performance attributes that we computed based on all the attacks that we've simulated. Of course, again, this table is extremely too many numbers on the table. Let me just highlight some aspects of it. So you can see in here, the statistical detectors, which are CUSUM and bad data, they almost immediately detect simple bias injection attacks. You can see that the time taken for detection is almost instantaneous, and their accuracy is 100% in this case, and pretty much, okay, 95%, 96%, again, very high accuracy. But these same attacks, these same detection mechanisms do not perform that well when the attack is actually targeting too many points. You can see that the accuracy over here is far too less. And they entirely fail to detect stealthy attacks. You can see that the TPR is 0%. They have not managed to catch the stealthy attacks. On the other hand, NoisePrint manages to catch all of these attacks with a pretty reasonable accuracy. But you can see that the detection time that it takes is way too high. This is in seconds. So you can see that it takes almost a good minute and a half or even 2 minutes in some cases to detect the attack. So these graphs basically show that these stealthy attacks have gone completely undetected. You can see that the residual never really crosses the thresholds, which means that these statistical detectors have not caught these stealthy attacks. So now that we have all these performance metrics computed, we can come to the point where we compare these detection mechanisms. So you can see that while the statistical detectors are able to very efficiently detect basic attacks like bias injections, they complete with a very fast detection time, they entirely fail under stealthy attacks. On the other hand, NoisePrint demonstrates a better overall accuracy. And this is probably because the attackers might not be able to replicate process and sensor noise, because those are pretty much hardware properties, which might not be as straightforward to duplicate. But NoisePrint seems to fall behind on its speed of detection. So now a few comments over here at this point on this performance. So the failure of statistical detectors under stealthy attacks is in some ways expected, because these attacks are devised such that they do not cause substantial changes to the residuals. In the case of NoisePrint, the longer detection time of this method might be making it a little less efficient for industrial CPSs like power grids, wherein you require pretty much immediate response to attacks and anomalies. But we saw the fact that its accuracy is pretty high. So this can be an important advantage, especially when it is used for CPSs such as water treatment, wherein the attacks might take a little longer to manifest and actually cause some physical harm. So before I come to the conclusions, I'd like to take a moment to mention some of the challenges and general comments throughout this work. Firstly, you saw the fact that our test beds were pretty much small-scale research facilities. So getting or creating a system model for these test beds was more or less a feasible task. And this might not be the case for actual real-life industrial plants. So in such cases, we might have to divide this large plant into several sub-stages based on what kind of process is taking place in each of them, and then having individual models for them. So this is one way we could counter the problem. Secondly, it is not really an easy task to get these reference models for some test beds that are very sensitive to environmental disturbances. So what we observed was that noise from the background on environment actually caused very unexpected and unpredictable deviations, especially in the case of WADI. So at times, these models might not be behaving as perfectly as we want them to, even under normal operation. Then one, of course, must have to ensure the fact that the sensors are not faulty or old, because this tends to introduce way too much noise, which hinders the creation of useful system models. And lastly, what we observed was that these system models itself tend to kind of perform in a very unexpected way when they're tested while the plants are on standby. This probably happens because the model creation process involved running the plants, and we did not really have a data set of the plant in standby. So this is probably one of the reasons that it failed to perform it failed to perform in a good manner under standby conditions. Then let me now present the conclusions. So we can say that these statistical methods that are CUSUM and bad data, they are very useful in the detection of simple attacks, which we gave an example as bias injection attacks. But when it comes to complicated stealthy attacks, we require a much more sophisticated technique, which could be NoisePrint in this case. And finally, we also would like to take this moment to emphasize the fact that while detection methods must have a very high accuracy, we must also take into account its time for detection of the attack, because in a real life scenario, this is a very crucial metric to ensure the safety of the surrounding economy of the CPS. With that, I come, sorry, I missed on one slide. So we'd like to thank SUTD's research grant for supporting this work and the authors for their valuable insight. And lastly, the iTrust Research Center at Singapore, whose facilities we have used throughout this work. And with that, I come to the end of my presentation. Thank you for your time.